Welcome back, everyone, to another fall semester. I hope everyone had a wonderful summer break. We are very happy to resume our bi-weekly seminar series entitled Civil Engineering for the Future. This is hosted by the School of Civil, Environmental, and Infrastructure Engineering at the Southern Illinois University, Carbondale. And we are very happy to present our speaker for the day, Dr. Debasish Jana. He is an assistant professor at the Department of Civil and Environmental Engineering at the Colorado State University. His research focuses on AI driven risk assessment and resilience planning for infrastructure networks, with a particular focus on natural hazards such as wildfires, landslides, earthquakes, etc. His main aim is to support data-informed decision-making and enhance infrastructure resilience. Before this, Dr. Jana was a postdoctoral associate at UCLA, and he obtained his PhD from Rice University. We are academic brothers. We had an overlap during our grad school, so we had some really happy times at the time. So I'm really excited to invite him, and I'm really looking forward to the presentation that Dr. Jana has to make. Debashish, over to you. And
Yeah,
sorry,
thank you
before
so
you
much.
proceed, sorry, Debashish, before you proceed, any questions from the audience, please leave them in the comment section, and Dr. Jana will be around to answer all your questions at the end of the presentation. Thank you. Over to you, Debashish.
Yeah, thank you so much for this great and kind introduction. It is like a really my pleasure to get invited from you all. And thank you so much for arranging this. So I'll be sharing my screen now. Uh, Let me know if there is any problem persists. So 1 second. Okay, can you see my screen? Okay, awesome. Okay, so today, like we'll be discussing about data to decisions. Like in here, so in general, we perform these kind of things in our everyday life. Like before going to office, we first think about what the weather is, and according to that, we dress. So the thing is that have you ever wondered that how the government make the decisions based on data, like after any disaster events, how they allocate the budgets for infrastructure improvement? So today I'll be discussing some of the work that I have been doing mostly in my postdoc at UCLA. So I have been assistant professor only for last 2 weeks. So yeah, so today I'll be talking about how we can use the data-driven strategies to enhance the infrastructure resilience. So nowadays, from wildfires to earthquake and floods, our infrastructure faces growing risks, and my research tried to address that. And thank you so much for joining in here, and let's get started. So you can see this map. This is the map of the California, and the small blue dots you can see in here, it's the highway bridges. There are over almost 13,000 bridges. Some of the key landmarks are this Golden State Bridge and also Bixby Bridge. If you have ever visited the Bay Area, you probably gonna be seeing these bridges. So when we analyze on the structures, we focus on the individual assets and their performance. But when we look at the infrastructures like road infrastructure network, we consider the whole network. That means if one of the bridges or one of the components get disrupted, it's not only the bridge, the full total systems get affected. The safety scale is very important. Instead of zooming in, we are zooming out and seeing the bigger picture and how interdependent these systems are when this resilience matters. So I'll be showing some of the different infrastructure networks which are very essential in our life. So first is road network. You can see that the key components of road network is like roads and bridges are really critical for this kind of infrastructures. They are designed by structural engineers. So as a structural engineer, I'll be talking mainly what are the components that get designed by the structural engineer and how these disasters can affect the infrastructure networks. So the second is power network. It relies on transmission towers, and these towers are designed by structural engineers. So it is very vulnerable to extreme weather, like a failure can lead to widespread power outages. And third is natural gas distribution network. There are underlying underground pipes and also transmission towers, which is designed by the engineers. And if it get failed, we also have like bigger problem. So primarily in this talk today, I'll be focusing on the road network, but some of the other work that I have been pursuing also with power network and natural gas distribution network. So the main thing is that why we are interested in this kind of studies. So the main motivation being the natural hazards in United States. We can see in here the United States has $1 billion climate problem. So this is the climate disaster cost all over the USA. You can see for Illinois, where you are coming from. So in Illinois, the cost, climate disaster cost in this last 45 years was 50 to 100 billion dollars. So for California, it was 100 to 200 billion dollars till 2024. But on 2025 January, probably you have noticed that there was a really big wildfire. This cost has been almost doubled after that. Texas, Louisiana, Florida, these states also go through severe storm and flood events, and that's why the disaster cost is really high. And the second motivation being the natural hazard index. So you can see the natural hazard index on this whole USA map, and this is color coded. You can see if it is very low, like the lower yellow color it shows the low hazard, and more red it goes, it shows the high hazard. So for Colorado, where I'm coming from, it's 20. I also checked for Illinois, it's also around 20. For Los Angeles, Miami, the hazard category is like around very high to high. So we have to notice these problems. Next, I'll be discussing like what are the inherent complexities. That means why this problem is super difficult to address. So first one is that the interconnected components, because one small disruption can cause cascading failure, which can cause and can affect the entire systems, and these infrastructure networks are highly connected. And second one is spatially varying risks. So what does it mean? You can see this is the map of California, and this map shows the earthquake risk in California, and the red locations shows higher risks, and the other colors, mild color, shows lower risk. So you can see the risk is spatially varying. And so when we're talking about a large region, like when you're talking about interconnected components or going through the full road network, it's very hard to model the risk for this whole region as it is spatially varying. And third is lack of high resolution data. For single structures, we can mount all these sensors, but when we are talking about state level or city level or nationwide structures like infrastructures like road network or power network, it's we have like very low amount of dense data like that. So that makes the analysis difficult. So this is the main framework, and I would be saying the disaster management cycle. So after a disaster, the response means immediate action after the disaster. Recovery means restoring infrastructures and communities. And after that comes mitigation, that means strengthening systems to reduce for future risks. And preparation means planning for the next disaster. So we can divide this whole management cycle in two halves. So one is pre-disaster risk reduction phase. That means before the disaster happens, you are taking some precautions so that if the disaster happens, it's not that big. And the post-disaster recovery, that means building smarter structures so that the failure doesn't repeat. So I'll be talking about my work in both of these things, but mainly I'll be discussing about this pre-disaster risk reduction phase. So what type of data I use? So you can see we have data from different sources. As I work on infrastructure network, I have this data like about say road network, which represents the connectivity, condition, and dependency of roadways, bridges, and other critical assets. Demographic, that means it provides the population information, population distribution. That means how many people are using this kind of network. There are different data sources, satellite data. As we are working with a really vast location, we need this kind of satellite data. LiDAR, which gives us very hyper local information, very dense information. Camera. So one thing to note about this camera has to be geotagged. Normal camera cannot do that. So we need GoPro or your mobile camera, which is geotagged. So when you are taking the picture, you know that at which point, at which geo-coordinated location this picture has been taken. And also for accelerometers, drone can be also used for vibration measurements for bridges. So today in this talk, I'll be mainly discussing about this infrastructure network, demographics, LiDAR and camera data. I have been also using satellite data for other projects. So before diving into resilience, I'd be like defining what is resilience. It's a combination of hazard, vulnerability, and exposure. So hazard assessments means identifying the potential events. Vulnerability means how the system get affected when this event happens. So say if in the Mars there is some quake happens, which is called Mars quake, our structures in Earth would not get interrupted for that. So this kind of interdependence is important. And the third thing is exposure or demographics. So if the system get failed in some kind of remote location where not many people are using that, would not be affected by that event. But if this event happens in the dense location like cities like in New York or in Florida or in California where there are lots of people, then this risk is very high. The resilience means ability to withstand the disruption. So this is this resilience curve. This y-axis shows the system performance over time. You can see that after one disruptive event, the system performance drops to a certain limit, and it takes some time to recover to get back to its original system performance. So our objective is to build one resilient systems so that when disruptive event happens, the amount of disruption is very low, and also it can get back to its original system performance as quickly as possible. So the key question to address is that how can we make the civil infrastructures resilient to hazards? So in here I am showing three GIF files. You can see in here for Los Angeles, California, there was a recent wildfire in the month of January. Second one is landslide in Tennessee. And the third one in Houston, Texas, there was a flood in Harvey. So personally, I have witnessed two of these events. So when I started my PhD in Rice University, I have witnessed this flood. And also when I was back in UCLA this year, I also witnessed this wildfire in firsthand and also collected lots of data. So this seeing this firsthand reinforced the urgency of my research. So that's why I try to develop some framework which can be applied to some natural hazards, and it can make better infrastructures and make the infrastructure resilient. So if this event happens again, the infrastructures cannot get affected as such. So first topic, I'll be talking about the resilient road infrastructures for wildfires, as it is like really recent event. It's like still in our mind. And this project is funded by US Department of Transportation, Caltrans, and Los Angeles Bureau of Engineering. So I'll start with this wildfire hazard and its impacts on the road networks. You can see these are the recent wildfires in Los Angeles. And you can see in this green, these hillside areas has really high vegetation. And when it has dense vegetation, and due to dry weather, they are highly susceptible to wildfires. So you can also see there are lots of roads, which is in white. And some of the roads are very narrow, and it makes difficult for the emergency vehicles to pass. Like when this kind of fire happens, people cannot evacuate properly, and the emergency vehicles cannot also access those locations. So it leads to traffic jam and slowing evacuation and response effort. The economic cost for this wildfire was almost 250 billion US dollars. So the key research questions I'm trying to address in here, how to optimally increase the road network resilience. But what are the steps? So I have mentioned that as some of the roads are very narrow, that's why it's create problem for evacuation, and also emergency vehicles cannot pass. So by optimally increasing the road resilience, we have to find out which are the critical roads we might need to widen, and we can address and we can say these things to government, California government and the city government, and giving them some lists of priorities, which roads we should widen. So this is the sample network of interest. This is Los Angeles hillside region. This is Santa Monica. If you have ever been in the Los Angeles, probably you can recognize. And in this red mark shows the hillside network. This star location shows the UCLA campus where I used to work. So this is a really big network. You can see it covers 120 square miles and there are 400,000 trips per day. So if you want to go from the Northern California to Southern California, you might have to pass this location. So we are modeling this network as a graph problem. The nodes are the road junctions and the roads are denoted as edges in the graph. And you can see this is a really big graph problem. The node number is like almost 8,700 and number of roads are almost 21,000. So even though I have performed this analysis on this big network for conceptualization perspective, I'll be showing it in on the smaller graph in here, a simplified graph. You can see these red dots are the inside nodes and the green dots means evacuation points. This golden boundary is the inside the golden boundary we have all the vulnerable roads. So now let's talk about how I am modeling this risk. So first we have to find out the what is the hazard, and hazard depends on lots of things when you're talking about wildfire. First we have to perform ignition modeling. That means where the fire can start. So those locations. And the second portion is the weather modeling. If the fire has started, then how it gonna be propagating? It depends on the weather condition. That means if there is high wind velocity or like low humidity, then the fire is much more vulnerable, much more like can get accelerated. The third step is propagation. That means how the fire will get propagated and how it will get spread. The fourth is the vulnerability assessment. That means if the fire gets propagated like that, which components would get completely blocked and you cannot use those things. So this vulnerability assessment has two steps. First is component level impact. That means which roads get blocked, and network level impact. That means if those roads gets blocked, what is their network level impact. And the last step is the enhancing resilience. That means which roads we should retrofit or widen in order to protect this. So I'll be discussing these steps in each of the slides, how I am performing this ignition modeling. This is completely data driven. So we first look at the previous fire scenarios. You can probably see in these red dots, it's showing the previous fire ignitions over the last 25 years. There are almost 154 fires, and understanding these locations can help us predict future fire ignition. So research shows that there's a strong correlation between the fire ignition and the energy release component. So in here for this block 5, I am showing the plot of this probability of fire ignition versus ERC. So ERC can vary from 0 to 100. This energy release component is dependent on the fuel model and also some weather condition. And in here we try to fit this. So now we know that where the fire can propagate. So just like this, for every of these grids we're going to be having this kind of probability distribution. You can see in the here for block 10 there is no past fires, because this is Topanga State Park and there are state troopers. If there are some kind of fires ignited, they go there and extinguish them. That's why in the past data there was no fire. So the next step is the weather modeling. So why the weather is important? Because the fire spread depends on multiple factors such as energy release component, humidity, temperature, wind direction and speed, precipitation and fuel moisture. Like for example, like in January, if there is dry condition, makes the fire spread much faster than in September when there is like wet condition in the state of California. So how we are performing this kind of, how we are modeling this kind of weather? We are using this generative adversarial network to model this kind of synthetic weather scenario. That means in the recent future, what can be the weather condition which can help the fire to be propagated? So in here you can see like in this kind of things. So this generator is creating this kind of weather models from random matrices. So probably you have heard about AI generated faces, which uses this kind of GANs. So this is the same concept. Instead of generating the faces, we are generating weather samples. And in here, how this matrix is evolved, like in here, this X direction is the days, and the Y direction shows all these different kind of components for different blocks. So when we have this weather modeling done, we have to know how the wildfire gonna get propagated. So for Los Angeles area, there is two different location, like two different part. One is called wildland domain and one is called community domain. What does it mean? There are some areas which is only having lots of trees, but there are lots of areas which is in the interface of the urban area and the wildland area. And fire doesn't get propagated same at the same in this two kind of domain. So you can see in here, when there is wildland domain, there is wildland fuel. That means the fire will engulf the trees or the associated fuel regarding that. But when it reaches the community, the fuel is brick or the other woods or other kind of things. So you can see in here, for our cases, so we are using Fire Area Simulator or Farsight, which is one free software, like open source software you can use. But we are also using Swift for modeling this WUI or Wildland Urban Interface to know how the fire would get propagated. So we are collaborating with University of Buffalo on this. So you can see when the fire comes closer to the wild and urban interface, we activate this module, and from there we propagate the fire like that. So this is the two instances. Like you can see, if the fire has started in here, how it's going to get propagated. You can see this green location, that means wild land model, and the red location means some of the urban components. And same for in here, we are starting the fire into different location to show how the fire can get propagated. And it's filtered by the red flag weather condition. That means if the wind speed is more than 25 miles per hour and the relative humidity is less than 15%, then the fire will get propagated like that. So now we have to find what are the vulnerable roads. That means which roads are very small. So we have some data from satellite or like the city, but they are not updated. So how to find the vulnerable roads? We are using these mobile mapping systems. In here, you can see on the top of this car, this is my advisor's car in UCLA, and you can see we mount one of these mobile mapping devices called Carta Stencil Pro, and it has 4K panoramic cameras which captures high resolution image, and this lidar systems which creates detailed 3D digital twin, and also it's associated with one GNSS or global navigation satellite systems, so that we can know that this kind of lidar data and this kind of camera images are captured at which particular location. So this is one sample point cloud for our from our traverse. You can see this is highly detailed. You can see all these informations regarding road, width, slope informations, height and terrain details. And this Carta Stencil Pro, one second. Yeah, this Carta Stencil Pro can capture up to 600,000 points per second and 10 hertz scanning speed. And it can also capture the data for 200-meter range. So we have to first know that in this kind of point clouds, which one is road, which one is slope. We have to segment these point clouds. One of the key challenges is that segmenting this kind of dense point clouds, because we don't have much data. Like there are lots of data for image segmentation, but not the point cloud segmentation. So what we have performed first the image segmentation, and we are projecting it to the lidar points. That's how we are making this kind of point cloud segmentation much more faster and really applicable to this. So you can see this is the world coordinate and this is the camera coordinate. By using these transformation matrices, we can accurately identify which one is roads, which one is slopes. And why I'm talking about slopes, because if we have to extend or widen the road, we have to know that which slopes we have to cut down. So this is the sample result. You can see in here in the left, we have this raw lidar scan with the color information. And in the right, we have labeled point cloud. The points in green shows the road points, and points in blue shows the slope points, and it can accurately measure the road weight, slopes, and elevation. So now we know that where are the vulnerable roads. If the road width is not as per the specification, we can consider those are vulnerable roads. The next step is the network performance. That means if this road gets blocked, how it gonna be affecting the full network performance. First one is safety. That means is the evacuation time smaller than the fire arrival time. So if you want to evacuate from one point, you don't want that the fire gonna be reaching to you very soon. So we have to evacuate people before the fire reach to them. The second one is connectivity. That means if there is any evacuation paths which are still operational. You can see in this image, after the fire has engulfed this area, for these 2 points, there is no way they can go out to the evacuation sites. They might need helicopter or some other means to get evacuated. Third one is reliability. That means did the shortest evacuation time increase? So previously, if someone has to go from this location to their nearest evacuation path, evacuation point, they could have used this small path. But as fire has engulfed this area, they have to take a longer route. And the fourth is efficiency. That means how did demand-based travel time increase? So when the fire has engulfed, there will be lots of people going to be using the same roads. So we have to know the population information so that we can address this kind of congestions. So now we are adding this kind of 4 parameters into this matrix, and it's called network performance tensor. I have talked about this safety, connectivity, reliability, and efficiency. They are demarcated in these rows. And you can see there are different kind of burn period, like at 0.5 hour or 30 minutes, what is the network performance? At 1 hour, what is the network performance? So this is also time dependent. And we are performing this kind of estimates for all these potential wildfire scenarios. So we have created this kind of data sets, like where the wildfire can happen, if this wildfire happens, how it can get propagated. So we have around 10,000 of wildfire scenario to work on that. So this is one example where I am showing that when the time propagates, the efficiency, the network performance matrices, the network performance values, these are going down for one kind of scenarios. So our objective is to minimize these overall performance indices, like in here, maximize this overall performance index, which is like a norm of this full tensor. So in resilience improvement for capital investment, our objective is to find the set of roads for optimal retrofitting where we are maximizing this given a budget constraints. So we can see in here that if we had $110 million, we could have improved all the roads, and the efficiency should be 1. But you can see only for $10 million, we are achieving almost 65% of this optimal efficiency, which is really a cost-effective solution. And for this kind of for $10 million, I am showing which roads we should improve. So next, I'll be talking about a little bit about the landslides, because in California, one other hazard which is predominant is landslide. In this area of Los Angeles, you can see the past landslide events, and it cost the government almost 3 to 5 billion US dollars per year, and there are almost 300 landslides per year. So this is one of the example. This is the landslides in Highway 1 near Big Sur area, which connects Los Angeles to San Francisco. So due to this kind of event, lots of people has to take a different route, or they have to detour for this. So that's why in here, the research question is that how to optimally increase the road network resilience. So previously, when I was talking about the wildfire, we had to know that which location we should increase the road width. For this landslide, we have to know at which critical location we should build the retaining walls. So the procedures and framework are the kind of same. So previously I was estimating where the wildfire can start or ignite. In here, we have to first understand that where the earthquake can happen. And the second is if the earthquake happen, what is the ground motion attenuation? And the third step is if this kind of earthquake happens, which roads are vulnerable and what is their network level impact. And the last step is enhancing resilience. That means at which location we should build retaining walls. So let's talk about all these steps one by one. First is rupture forecast modeling. That means where the earthquake can happen. The earthquake can only happen on the top of the faults. So we have modeled, we have known that at each location the earthquake can happen, so which will create almost millions of events. And if this earthquake happens, what is their ground motion, ground attenuation or ground motion intensity if this kind of event happens. So we have captured that by attenuation models. So now, as we have this kind of catalog where the earthquake can happen and what is their ground motion distribution, the next step is that which of these roads will be vulnerable for earthquake-induced landslide. So how do we know that what's the vulnerability, earthquake induced landslide vulnerability? This is dependent on the yield acceleration coefficient, and it's dependent on the soil parameter and also slope parameter. Soil parameter means cohesion and angle of internal friction, and the slope parameters means slope angle and slope height. So it has been in the research, it has been shown that if the cohesion of the soil goes high, the landslide probability goes down. And if the angle of internal friction also goes high, goes like up, then the landslide probability will also go down. But for the slope angle and slope height, if they are high, the landslide probability is also high. So you can see in this map, in here we show the blue shows the ky or yield acceleration coefficient of 1. That means the landslide probability is very low. But in the middle portion where there is like much more mountainous region, there is like high landslide probability due to earthquake. Now there is like millions of events I'm talking about in here, and I have mentioned that there are lots of faults in the California area, so millions of earthquake can happen. So how to calculate this kind of network performance? It has been very difficult. Like network performance, we're talking about total system travel time. That means if the network gets interrupted, what would be the delay? So that's why we have proposed one machine learning based model, which is called Siamese graph convolutional network model. So what it does, it takes the original network and it takes the damaged network and outputs the network performance loss. So in general, if we have to perform this conventionally, it would require the traffic assignment problem. And for big networks, this traffic assignment problem is extremely computationally inefficient and it would take lots of times. And as we're talking about millions of simulations, it's not possible for us to perform that. So why we're talking about this Siamese network? So as a Siamese twin who has two heads, you can see we have these two heads and the same body. That means all of these things are going to the same network architecture and it's giving us the network performance loss. We have shown that previously there was one state of the art model which uses artificial neural network, and we are using this proposed Siamese graph convolutional network. It has less number of parameters and also has better performance. So now let's talk about this resilience. Now which locations we have to build this kind of retaining wall. So there are total 6,500 roads which is vulnerable for this kind of earthquake induced landslides, but the government cannot improve all of these roads, right? That's why we have to find the set of optimal roads for retrofitting. We have to minimize this network performance loss given a budget. That's how we have found by using genetic algorithms, or you can use any other optimization to perform this kind of optimization, like which locations we should improve. So you can see to improve this 6,000 roads, we need $610 million, but only in $10 million, you can achieve the 95% of the total performance. And these are the roads where I'm showing that for $10 million, which roads we can retrofit. Now, whatever I am saying, why do you believe me? We have to know some validation, right? So I am validating these methods by validating using risk curve. So what is risk curve? It shows the network performance loss in the x-axis, and in the y-axis, it shows the annual rate of accidents. So that means, so this is So our objective for retrofitting would be to pushing this risk curve towards the southwest direction. That means same amount of loss would be happening less frequently. So that's what is the objective being. The same level of network performance loss would be happening but less frequently. So we have seen that more amount of budget we are adding in here, the risk curve monotonically goes towards the southwest direction. So this shows the validation of our work. So in here, our research is not only limited to academic exercise. As we are getting funded by Los Angeles Bureau of Engineering, we have to deliver them some kind of software and web application. We have done that in here. I'm going to be showing a little bit about what the software and web app looks like. You can see we have developed this hillside street prioritization application, and in each of these areas, each of these streets can be composed in importance, condition, and hazards. We are looking for the roads which is having high importance and bad condition, and you can see in here they are got highlighted, and we can validate those things if they are really in bad condition or not. We can go to the streets view, and you can see in the Google Street View these roads are like really narrow and in bad condition, even though they are critical road components. And some of the areas the Google Street View has any data, and that's why we have driven through these areas, and we can see there are lots of bad roads. We cannot believe that sometimes that this is the roads of Los Angeles. So also, as we have collected LiDAR data, we also give the LiDAR data sets to this web page. You can see from here, you can drive through and also can measure what is the road weight, the slope angle, slope height properly. And also you can write some codes to understand at each location what would be the road width and slope heights and slope angles, all these things. So the next is the other key research achievements, which I'm not going to be discussing in details, is that previously I was only talking about pre-disaster resource allocation. That means before the disaster is happening, I was talking about what could be the potential disaster scenarios and how to address that. Now I'll be talking about the post-disaster scenario or the mid-disaster scenario. So the critical question is that in the middle of the disaster, where should we optimally invest the budget? So you can see in here, this is the simplified road network, where I'm showing that for there are two critical roads, critical edges, I would say, that it's E1 and E2. When in the middle of the disaster, this E1 has broken, which becomes the most critical? E2. Because if it breaks, it will create a two different type of like cluster, and there would not be any connections. So this is in the middle of disaster, but for these really big networks, it becomes highly difficult to understand this kind of things like which roads are important right away. The second one is the what is the order of the repair. You can see in here for this small network, E1, E2, and E3 are interrupted, but we have to prioritize them, which one to repair first. So in general, there are some algorithms, some graph-based algorithms, edge betweenness, centrality, vulnerability. They are of order like second order polynomial. So E, like the modulus of E means like number of edges, modulus of V means number of vertex or nodes. You can see using this vulnerability, this is order of polynomial order 3, but I have proposed one graph neural network based techniques. After training, the inference step is in the linear order. So for bigger networks, it is very easy to understand what are the critical components. One of the other work I have been doing is optimal transformation to complete streets. What does complete streets means? That means mobility for all. That means in here you can see for mass transit, for cars, there is also one lane for bicycle, bikes, and also it has ADA compliant, and also there is pedestrian walk. So most of the roads in Los Angeles aren't like complex streets, but as you know that on 2028 there would be Olympics, and the Los Angeles Bureau of Engineering and city government wants to make most of the roads like that, but they cannot improve all these roads because Los Angeles has almost 7,600 miles of livable roads. So we have to understand where to like make this kind of changes. So these changes are very like tough for optimization, because if you allow some kind of bicycle path, you are also compromising the like the road for the cars. So we have to know all these things. So I am performing this work with the collaboration with US DOT for this. So we come to the summary of our talk. So the objective is to get actionable insights to strengthen the infrastructure's due to natural hazards. First, we are estimating the conditions from this kind of sensing techniques like cameras, lidar, or satellite, and we have to find out the importance of this network using graph convolutional network, graph neural network, or some graph-based algorithms. We are addressing risk for different kind of hazards. Primarily, I have talked about earthquake-induced landslides and wildfire in here, but I am also performing this similar kind of research for other hazards as well. And we are passing all this information through some optimization framework and giving the ranking to the decision makers or stakeholders, like to which assets to improve, to so that we can get one improved infrastructures. So the future direction of my work is like optimal capital investment for post disaster scenarios, like sequentially where we should invest the money. And the second thing is that for multiple correlated hazards, so when I was talking about these landslides and wildfire, they were not correlated, but when you're talking about post wildfire debris flow, they becomes correlated, and we have to address how it gets affected, how it affects the infrastructures, and how we can address the problem. And the third thing is that multiple infrastructures. So when this event happens, like wildfire or flood happens, it doesn't only affect the road network or water network or power network different, like independently. It affect them together. So we have to address when there is dependency between water, power, and road infrastructures, and how a city management or government or the state government can invest this money to different kind of infrastructure agencies. So with that, I'd like to thank you all for joining this. So this is one of the pictures. So this is the first time I came into the TV for our contribution to this Los Angeles like Bureau of Engineering. They have given us award. You have seen my me in here. This is the PhD student, Dr. Sven Malama, I have worked with, and this is my supervisors at UCLA, Dr. Sriram Narasimhan. And this work has been funded by US DOT, Caltrans, and CEC, California Energy Commission, Los Angeles Bureau of Engineering, and ITS, or Institute of Transportation Studies. Thank you so much, and I like to take some questions.
Thank you so much, Debashish. That was a wonderful talk.
Thank
Thoroughly
you.
enjoyed it. So let's open up the stage for questions. Anyone from the audience?
So is there any comment box where I can see all these questions or something, or you're gonna be talking the questions in here?
Uh, so typically people leave it in the chat. So far we haven't seen any, but
Okay.
uh,
Okay, Devashi, before like students are asking, let me ask one question.
sure.
So thanks for a good presentation, Devashi. Like really
Thank
nice
you.
presentation. And so what are your thoughts when you're talking about like what kind of a research idea you have about this post wildfire debris flow and like what you're thinking in this particular one of my student, he is here in the chat, maybe he'll ask some questions. He is working on the post wildfire debris flow. So I mean, what are your thoughts in this research area?
So currently, I am collaborating with UCLA regarding this post-wildfire debris flow. We have the immense amount of data for this Palisades fire and Eaton fire, which happened in Los Angeles, and lots of geotechnical engineering professors and faculty students, they have gone there and taken the data, like how the soil properties has changed. So
Mhm.
from this soil property, changing the soil property, we can also find out what is their landslide potential for next rain if the rain happens, and also how
Mhm.
much vulnerable they become. So for
Mhm.
us, our cases, as the already wildfire has happened, we can only use the data-based techniques to understand where are the landslides can happen and how can they affect the other infrastructures. So that is the
Mm-hmm.
thing I am now currently working on. But we can also take it further. Even so, for Los Angeles area, already the wildfire has happened. For some cases, like in Colorado, the some of the cases wildfire is not has not happened yet, but some of the areas are vulnerable. So we can
Mm-hmm.
consider like in which locations the wildfire can happen and how their soil property can change. So we have
Mm-hmm.
to, yeah. So this is like becoming one really nice collaborative project because it
Mm-hmm.
requires the expertise from different domain. Because as a structural engineer, I don't know how the wildfire affects the soil. So I
Mm-hmm.
am collaborating with Professor Idil Akin in UCLA.
Yes. Mm-hmm.
So yeah, that's
No, okay, okay, got your point. Yeah, because my point was the same. Like it is mostly a geotechnical engineering program problems. Like what is as a structural engineer, there is a contribution. So I was just thinking about that, but it's all about the data-based decision making process. Okay.
yeah, yeah. So as a structural engineer perspective, I think the risk analysis perspective to the infrastructures, how it get
Mm-hmm.
affected, that's mainly one of the structure thing. And
Mm-hmm.
also like performing this kind of simulations, like where the landslides can happen, that becomes one of the data science based like work.
Got your point. So, do you have any idea? Like, is there so like the main cause is like when there are roots or the vegetation, they control those upper layer and they like protect from the debris flow. So, do you have any idea like any technique which we can apply to assess the vegetation, like how much vegetation it burn and something? So, do you have those ideas, something?
Yeah, yeah. So I am also working in the same project regarding that. So we are having
Mm-hmm.
this kind of satellite data for different
Mm-hmm.
location and also how the wildfire has propagated over the time. And we also
Mm-hmm.
have one fuel model called Fuel Vision. So it is
Mm-hmm.
done by one of our advisors in UCLA, Dr. Ertugrul Tasiroglu. So from this
Mm-hmm.
Fuel Vision, from the satellite data, you can know how much fuel is there and how much what is their ignition probability and how much heat they can carry, and you can get some
Mm-hmm.
idea that if this area is having too much ndvi or this much
Mm-hmm.
amount of fuel, how much they can burn and they can affect. So we are using also satellite data because there are lots of areas like around 15,000 acre got burned, and it's very difficult to find this kind of the data from this full area using this kind of mobile mapping systems. So we are also using satellite data to understand and get the information about which areas has burned and what was their fuel model, and from there we can interpolate further studies.
Okay. If I may ask just one last question before people are sending those questions. So, soil is a very heterogeneous material, and when we talk about the soil heterogeneity, it's very hard to replicate in any model because either you can go with the like elastic model, maximum elastoplastic or elasto viscoplastic at the maximum, but the heterogeneity in soil is a wide range, and so how you what kind of a correction factors or things you apply in your data-driven approaches to account the heterogeneity of a soil?
Yeah, yeah. This is a really good questions because I don't have any answer for this. I
Okay,
am not
okay.
a, yeah. So the thing is that I am relying on the professors in
It
UCLA
is,
who
yeah.
are like soil
Uh,
mechanics expert to tell
uh,
how it get affected after the fires. Yeah,
got your point. Got your point.
yeah.
Okay, thank you. I think, okay, so let's open this floor for all the students. If you have any question or the participants, if you have any question, please send there in the chat. Mm, can we allow Devashi for if
Yeah,
they
yeah,
want to
yeah, sure.
talk?
Yeah,
Yeah,
yeah, let's do that. Yeah.
yeah.
Feel free to unmute yourselves
Yeah,
if you have
I
any
think they
questions.
can't unmute themselves,
Oh,
but they can just raise a hand
raise
and
their
then we
hands
can
and yeah,
allow.
yeah,
Yeah,
we can.
then we
Yeah,
can allow.
yeah. Oh, there is one question from Subhash Pageni.
Mhm.
Is there any possibility of getting involved in any of your research work, Dr. Jana?
Yeah, so currently I am recruiting like PhD students, but I also open to collaborations. Yeah, so of course, like there is like lots of potential projects that I'm working on, and of course, like if you are interested, please feel free to send me an email. We can chat in detail via Zoom or Microsoft Teams. I can also add my email ID in here if anybody is interested to talk about, and we can meet, of course.
Mhm.
Okay, I had one question actually. So, in all of this work that you have done, you have used a lot of optimization algorithms, and clearly the kind of networks that you're using, they're pretty massive,
Yes.
as I understand. So, did you run into any issues with traditional optimization algorithms, and are you planning to use anything different in the future when, let's say, you include, multiple types of infrastructure or correlated hazards, so on and so forth?
So currently I am working on reinforcement learning techniques, which becomes a little bit easier for us to handle, but I'm not sure. So I am currently using normal reinforcement learning. I can also go to graph reinforcement learning if they can handle it much better. And in the previous work that I have been showing, I have mainly used genetic algorithms. It took a little more time, but it showed occasionally good result. But yeah, if you have other suggestions for like effective optimization algorithms, please feel free to talk. Like I can also use those algorithms in my research.
Oh, I would love to talk more about it with you. Like offline, we can do this. I mean, that's one
Okay.
of the things that I am also very interested in. So happy to talk. All right. Thank you so much. Okay, we
And
have
probably
Irfan.
I'm going
Oh,
to approach him too, like to write some NSA proposal or something, because our research really overlap a lot.
That's great. Yeah, yeah. I am also
Yeah.
really interested in that.
all right. Irfan
Yeah,
has a
Irfan, go
question.
ahead.
Yeah.
Irfan, you can unmute. I allowed you. I think he can unmute. Irfan, do you have any question? I think it's not there.
Irfan, if you're unable to unmute, you can just leave the question in the chat. Dr. Jana will answer your question.
I just left the question.
Oh, yeah, sure. Yeah,
Oh,
yeah.
I'm sorry.
permission you can ask.
Yeah, it's because I have a class actually, so now I have to leave. That's why I just
Oh,
left the
okay.
question on the chat box. Yes.
Okay.
So Dr. Jana, it was very wonderful and a very nice presentation. It was very impressive to me. So because I have a class soon, so I just left my questions. Maybe I can follow up the answer your answer later. So thank you, thank you.
Okay, okay. Thank you,
Yeah,
thank you. Thank you. Nice meeting you. Bye.
yeah, yeah.
So yeah,
Dr.
so
Janet, there is a questions in chat. Two
yeah, yeah.
questions. Yeah.
Yeah, so it was super wonderful presentation. Thanks, Dr. Jana. It seems that the graph theory metrics were used to quantify the road network. How did graph matrices specifically contribute to modeling cascading impacts? Also, data-driven research is challenging because obtaining reliable data is not easy. Many agencies and companies may have such data. How were you able to collect the data for this study? Could you share some tips on data acquisition or how you establish contact with relevant organizations? That's a really great question. So first, let's answer how did graph matrices specifically contribute modeling cascading impacts? So for our cases, as I was talking about, for full graph network, it's very difficult to calculate these critical roads. That's why I have developed these machine learning techniques. Even though graph is changed a little bit, we can understand how the network performance has changed. The thing is that data driven research is challenging because obtaining reliable data is not easy. I completely agree in here. So we collaborated with Los Angeles Bureau of Engineering and they have given us one permission letter where we have also, because the thing is that it's not always easy as we are going to lots of areas. We have collected the data almost for 400 miles in the Los Angeles area. So in each of the weekends, I used to go with my PhD students. Sometimes my advisor used to come and we have to drive those data with this mobile mapper with in the hillside roads, and sometimes people would object because they are saying that this is violation to their privacy. So we had to show this document from the city that we are improving that, but most of the peoples were very interested. They thought that we are Google Street View like modelers, but we are talking about this is about one research. So there is like you have to collaborate with the local government, otherwise you cannot do this kind of research, and the government has to allow that. So our work was in the collaboration with USDOT, Caltrans, and Los Angeles Bureau of Engineering, Department of Transportation. That's how we got this kind of access to collect this kind of data. And also, okay, then Obia Bucci mentions interesting contribution apart from generated satellite data? Are there considerations for data generated by community engagement to spot exact dangerous areas in order to run less costly optimization? This is also one great comment, I would say. So we have also collaborated with lots of community development platforms. So there is one I think platform called IC Change. So what happens when this kind of flood happens, they go to this community to help them. So what we thought about for this flood and all these things, we have some of the cameras. We sometimes go there and give it to them. If these things happens, they can mount it in proper location. We ask them how to use those things. But things that for California and Los Angeles area, there is only one hotline number. If you are complaining to them, then the government is coming to you. But the thing is that those numbers is not accessible to everyone. So people sometimes forgets to complain, and that's why some of the areas are very underdeveloped. So but our algorithms and our research shows that when we have this kind of data properly, we don't have to rely on whoever is calling and complaining. We can, the government can benefit and repair the roads and other infrastructures properly. So of course, if we have this community engagement, we can of course run like proper optimization techniques. Okay, so Irfan mentioned, Professor, how do you know that a specific algorithm suits best for an encountered problem? Okay, that's a really good question. And here, so the thing is that, yeah, please allow me to unmute. So the thing is that for me, we have to first know that how the optimization algorithms works, because there are lots of different suite of optimization algorithms. You have to find out which is specific, which is best for your problems. And also there is lots of validation. Like if the optimization algorithm is giving you some weird results, probably you're going to be knowing that this is not working for your optimization. Because if say for California area, we know what are the main roads which has like lots of traffics. If in our algorithms or optimization it says that these areas are important, probably we have some validation checks. So we, as we have these real life validation checks, that from there we can understand whether this optimization algorithm is performing properly or not. And yeah, Irfan, you can also speak if you want to.
I am guessing he still can't unmute. So yeah. Um, any other questions from the audience? If you have any other follow-up questions, Dr. Jana has left his email ID in the chat. So please feel free to contact him with additional questions. I'm sure he'll be very happy to answer them. With that, again, thank you so much, Debashish. This was a wonderful presentation. I thoroughly enjoyed it, and I hope all the audience really enjoyed it and learned from it. And I look forward to collaborating with you in the near future. Uh, and so, again, thank you so much for doing this on such a short notice. Really appreciate it.
Yeah. I thank you all for joining, and also thank you, Dr. Sen, and thank you, Dr. Tiwari, for inviting me on this. I also thoroughly enjoyed this. And so it was like I kind of say this is my like job talk, I would say, like for my all this last year I have been preparing for these job talks, and this was kind of one snippet and some of the sections that I was presenting. I hope that in near future I'd be doing some research as an assistant professor, and in the near future I hope I'll also get invited for this talk maybe next 1 or 2 years. Thank you so much.
All right, Dr. Tiwari, do we have any announcements for any more upcoming?
Yeah, so yeah, thanks, Dr. Jana, again. Like, I mean, I really appreciate in a very short notice you accepted our invitation and be the first presenter of this fall semester 2025. I thoroughly enjoyed it, and like, I'm sure like you ignited a lot of minds today, and they are definitely going to use your research, and we will definitely going to invite you for the future webinars for sure. For the others, like we are going to have our next webinar week after the other week. So like in the like after 14, 15 days. So on next Wednesday, on the same time, we are going to invite. As of now, we are working on the speakers, so I don't want to announce the like final name, but yeah, we'll meet again next for our bi-weekly seminar and webinar, and we'll discuss more on the research, most probably from the water resource side.
And just to add one more thing, this session was recorded, so we will post this on our YouTube channel. So if you want to revisit this presentation again, please feel free to do that. We'll post it on LinkedIn.
Mhm.
All right, with that, thank you so much, everyone, for attending this talk. And thank you again, Dr. Jana. This was wonderful. Have a nice day, everyone. See you.
Yeah. Bye. Thank you.
Bye.
Bye.